Again, welcome to Mathematical Structure for Computer Science. This is CS 113 course for Pace University, also known as Discrete Mathematics. In these lectures, we're going to continue with our graph theory in Discrete Mathematics. And in these lectures, we're going to learn about adjacency matrices, how we can convert a graph to adjacency matrices. So our main objective again is to go through what is adjacency list, adjacency matrices, and also incidence matrices. So first we start with the definition of an adjacency list. And here we said an adjacency list can be used to represent graph with no multiple edges by specifying the vertices that are adjacent to each vertex of the graph. So we said two vertices are adjacent if they are connected to the same edge, as we mentioned earlier, the previous lectures. So here our definition is saying an adjacency list can be used to represent a graph with no multiple edges by specifying the vertices that are adjacent to each vertex of the graph. So an example here, we have a graph with vertex A, B, C, D, E, and we have the edges connected. Now we can convert this graph to adjacency list. So that's table 1, an adjacency list for the simple graph, the first graph. So first we start with the vertices. So the first column will be the vertices, and the second column will be our adjacent vertices. So when I'm at vertex A, I can see that I have edge between A and B, and I have another edge between A and C, and I have another edge between A and E. So my adjacent vertices will be B, C, and E for A. Because we said an adjacent vertex is vertex that have a common edge or edges connected to them. So here we can see that the adjacent vertices for vertex A position will be B, C, A, because we have an edge between A and B, an edge between A and C, an edge between A and E. Now, when we stand at vertex B, we have only one adjacent vertex, which is A, because B is connected to only A. So in B, we have A. Now, when we go to C, we have edges between C and A, C and E, C and E, D. So at vertex C, the adjacent vertices will be A, E, and D. So in C, we have ADE. Then when we are at D, we have edges between D and E and D and C. So the adjacent vertices for D will be C and E, and that's our C and E. And the last one is the vertex E. In vertex E, we have edges between E and A, E and C, E and D. So at vertex E, we have adjacent vertices A, C, and D. So this is the concept of adjacent list from our simple graph here. So we can see the definition gets said, an adjacent list can be used to represent a graph, and that's what we just did, with no multiple edges. This graph doesn't have any multiple edges by specifying what the vertices that are adjacent to each vertex of the graph. So we have vertex from A to E. We specify A to E. At A, what are the adjacent vertices? We list all of them. At B, only A, we list it. At C, we have ADE. When I'm C, there's edge between AC, AE, and AD. So we have C, we have ADE. At D, we have edge at E between E and D, between C and D, and it's only 2. So you can see that at D, we have only 2, C and E. At E, we have 3, E and A, E and C, E and D. So it will be DCA, which is DCA. Now let's look at the second example. Also the same concept, but this time we have loops. Our first graph is undirected. This graph now is directed, but again, it's the same concept. we are looking for the adjacent list. So let's start with A now. When we are at A, we have A to B. We also have A to C. And we also have A to D. We have to look at the arrow. I'm looking at the arrow. And also we have A to E. We can see the arrow is moving. The direction of the arrow is from A to E. So that means the adjacent vertices for A will be B, because we have the direction of the arrow going from A to B. And also C, because we have a direction from A to C, the arrow. And also D, because we have a direction of arrow from A to D. And also E, we have a direction from A to E. So that's the 4, B, C, D, E. We have to be careful with the arrows. Undirected, we don't care about arrow. There's no any arrow, so we can just, when we see the connection, we just go through. Now let's look at B. At B, we have a loop. So that means we at B, but we also have a vertex B as adjacent to B itself, because it's a loop. We go and come back, we move away from A, B, and come back to B again. Then we look at the arrow. You see, this time we didn't say we have that, we have at B, we have B to A. No, the direction of the arrow is A to B. So A rather have a vertex of B, but B is not a vertex of A. So we have only B here. We look next arrow, A to E is opposite arrow, so it's not a vertex. The arrow rather is from E to A, B, not B to E. But we have one here, B to D. The arrow is going from B to D. So only 2 adjacent vertices we have here, B and also D. The reason why B, because it's a loop. So B and D. Then we look at C. First of all, we have a loop at C. So we have C. Then we look for the directions. From C to A, we have 1. Then C to E, no, is different direction. But we have C to E here. So E is some 1. And I think that's it. So we have ACE for vertex C, the adjacent. And also we look at D. At D, the arrow is going opposite from D to E, so it's not an adjacent vertex. And A to B to A is not a variable, it's B to A to B rather, the direction of the arrow. And D to B also is not good. The direction is from B to D, not D to B. So that means vertex D does not have any adjacent vertices. Or here they use the term terminal vertices. Because all the arrows are going towards D. They are not going away from D. When it's away from D, then we have a vertex. Towards D, rather E have a vertex for D, but D doesn't have a vertex for E. So let's look at E, the last one. So we have E going to B, the direction. So we have B, and E is not going to A, rather A go to E, so we don't have A. We have E going to D, so we have D. And we also have E going to C. So vertex E have 3 adjacent vertices, which is B, C, D. So this would be what we call the adjacency list. Adjacency list consists of all the vertices in the graph and their adjacent vertices or terminal vertices. So now, how do we represent a graph as an adjacency matrix? So first, we represent a graph as an adjacent list. Next, we are going to represent a graph as an adjacency matrix. So the definition said that, suppose that we have a graph which consists of a vertex V and edges A. And this graph is a simple graph where the absolute V is equal to N, which means the number of vertices. Arbitrarily, list the vertex of G as V1, V2 up to Vn. So the adjacency matrix AG of G with respect to the listing of the vertices is the n by n, which is the size of the adjacency matrix, 0 and 1 matrix. In adjacency matrix, the values are only ones and zero. There will be a 1 if there's an edge between the two, because we have a vertex matrix, which will be rows and column. So intersection of rows and column, if those two vertices have an edge, which means it's an adjacency matrix, we put 1. If there's no edge, we put 0. And that's what the definition means. Actually, in summary, we can say it here. So if I'm at A, ij, this will be an element in the matrix. I will put 1 for aij only if there's edge between those two vertices, which is bi and vj, if there's an edge. If there's no edge, I'll put 0. So in other words, if a graph adjacency matrix is ag, and a sub I and j is the element in the graph ag, then we put 1 when there's a vertex, there's an edge between the two. And we see an example here which will help us. So let's look at this example. Let's move this down. So the example here, we have a graph. This graph has vertex A, B, C, D. A, B, C, D. And we can see the edges. First, the size of the matrix is the number of vertices you have. So the vertices we have here is 1, 2, 3, 4. So which means I may have a square matrix of 4 by 4. So you can see that we have 4 columns and 4 rows. Why we have 4 columns and 4 rows? Because we have 4 vertices. Same thing, the second one, we have AB, same ABCD, so it's 4 by 4 also. So that's the first thing we should know. Converting a graph to adjacency matrix, the size of the matrix should be the number of vertices you have in the graph. Secondly, the first column, second column, third column, fourth column, first row, second row, third row, fourth row. Now, the first item is 0 here. Why? Because this means the first element and the intersection between the first matrix, which means if I'm here 1 by 1, that's first row, first column, I only need a loop to get 1 here, which means from A to A. Now we represent the ordering of, which is very important. We represent the order of the matrix element as A, B, C, D. So the first column and the first row is A. So if I'm at A and I move to A, which means it's a loop. Since I don't have no loop, I'll put 0. If there's no any edge, you put 0. Now I will go to the first row, second column, which means what? Again, I'm in the first row, which means I'm still in A row because my rows will be A, B, C, D. My columns will be A, B, C, D. So second column will be B and the first row still. So this means I'm at AB. And AB is 1. Why? Because I have A to B, we have an edge. So it's 1, A to B. Now I'll go to the first row, third column, which means I'm still at A. And this time, let's see if there's edge to C. Third column is C, A, B, C, D. So AC, oh, okay, AC I have 1, so I put 1. There's 1 edge, so 1. I'm still in A, and this time I'm in the fourth column, so it will be D. So let's look, A and D, we have an edge. There's an adjacent. So when there's an adjacent, we represent it by 1. Now I'll move to the second row, which means now I'm standing at B, vertex B. Now I'll look if there's a first column will be A, and the row is B now. So B1, B to A is 1, so we have 1. Now, second row, second column is BB. There's no loop, so we have 0. This means BC, second row, third column C. BC, there's an edge, so there's 1. Then we go to BD. Fourth column will be D, second row B. BD, there's no edge, so it's 0. there's no edge in BD, so it's 0. Then we go to, now we are going to stand in the C. So C is the third row. CA, there's an edge, so it's 1. CB, there's an edge, so it's 1. CC, there's no loop, so it's 0. CD, there's no edge, so it's 0 again. Then the last one is the D vertex. We are in DA. Okay, there's one edge, so 1. And now we go to DB, there's no any edge, so it's 0. We go to DC, there's no edge, so it's 0. Then we go to DD, there's no loop, so it's 0 also. So again, this is how we convert a graph to adjacency matrix. The order is very important, and so we specify that it's ABCD. So here we say when a graph is sparse, that is, it has a few edges relative to the total number of possible edges, then it is much more efficient to represent the graph using an adjacency list than an adjacency matrix. So we saw the adjacency list, and this is the middle. But for a dense graph, which is include high percentage of possible edges, then adjacency matrix is preferable. If you have a lot of edges in a graph, matrix is preferable. If you have less edges, then adjacency list is preferable. Other adjacency matrix on the list. So the second also is the same step as the first one. The order is A, B, C, D, and we have the same number of edges. I mean, the number of vertices is 4, so it's 4 by 4. So there's no loop in A, so AA is 0. I'll move to the second column, first row. AB is 1, we have edge. AC also is 1, we have edge. AD, there's nothing, so it's 0. I'll go to the B vertex, second row, and I'll look at BA, the first column is 1. And BB, there's no loop, so it's 0. BC, there's no edge, so it's 0. And BD, we have an edge, so it's 1. Then I'll move to C, the third row. So CA, there's an edge, is 1. CB, no edge, 0. CC, there's no loop, so it's 0. CD, we have an edge, so it's 1. And the last one is D. So we start with the DA, there's no edge, so it's 0. DB, we have an edge, 1. DC, we have an edge, 1. Then DD, there's no loop, so it's 0. So here we say that adjacency matrix also can be used to represent graph with loops and multiple edges. So as I said, with the loops, the diagonal section will be 1. So if I'm in at A and A, 1, B and B, 1. So the diagonal will be 1. And also a loop at the vertex VI is represented by 1, as usual. And also when multiple edges connect the same pair of vertices, that's VI and VJ, or if multiple loops are present at the same vertex, the IJ entry equals to the number of edges connecting the pair of the vertices. So we have to count it, the number of edges. So let's see an example here. The order again is the same as the previous, A, B, C, D. We have 4 vertices, but this time we have a lot of edges, number of edges. So first of all, since it's 4 vertices in the graph, we have 4 by 4 matrix sites. So the first thing we do, let's start with the first column, first row. So we are at A, and we see if there's a loop. There's no loop at A, so it's 0. Then we check, we go to the second column, so we check from A to B. Well, A to B now is 3. Why? Because we have 3 edges. This is undirected graph. Now, if we have a directed graph, then we have to look the arrow. If the arrow is moving from A to B, then it's 1. If it's moving B to A, then it's not. So here, undirected graph, all the 3 edges, we have 3. Then we look at A to C. This is our C, there's nothing, so it's 0. We look at A to D, we have 2 edges, so it's 2. Then we move to the B position. We check from B to A. B to A, this is undirected graph, so A to B, B to A is okay. So we have 3 again. Then B to B, there's no loop, so it's 0. B to C, we have one edge, so it's 1. B to D, we have one edge, so it's 1. So now we move to C, third row. First column, we look at the C and A. C and A, there's no connection, so it's 0. There's no an edge. Then C and B, we have only 1. And then C and C, we have a loop now. We have one loop, so it's 1. One loop, 1. Then C and D, we have 2 edges, so it's 2. And the last is D. We check with D, first column with A. So D to A, we have 2 edges. D to B, we have only 1. D to C, we have 2 edges, so it's 2. D to D, there's no loop, so it's 0. So again, this is the whole concept of, again, converting a graph to adjacency matrix. And also went through the converted graphs to adjacency lists. So here we say adjacency matrix can also be used to represent directed graph. As we said earlier, the directed graph doesn't matter. We only look at the direction of the arrow. So let's go back to our previous example. If, for example, here A to B, we have 2 arrows pointing to B, then from A to B, we are going to have only 2 instead of 3. Then the middle arrow is pointing from B to A, then BA will be 1. So we have to look at the arrow direction. So here we say the matrix for directed graph, which has vertex and edges, will have 1 in each I and J position. That's the rows by column position. If there's an edge from VI to VJ, where VI, V1, V2 to Vn is a list of vertices. In other words, the same concept as undirected. If I'm at Aij position, we get 1 if there's an edge between. But remember, the edge will give you the direction moving from the first to second, not second to first. Otherwise, we put 0. So the adjacency matrix for a directed graph does not have to be symmetric. It does not have to be symmetric because there may not be an edge from VI to VJ when there's an edge from VJ to VI, as we saw it. And this is the example I'm giving. If I have 3 edges here, there's 2 arrows pointing from A to B, and maybe the middle one of the edge will point from B to A. So you don't have to be symmetric. Symmetric means both parts or both positions opposite are the same. And also to represent directed multigraph, the values of A at position I and J is the number of edges connected VI to VJ. So representation of graph again. Next, we move to the incidence matrices. So again, in these lectures, we are going to represent a graph either as a adjacent list, adjacent matrix, and also incidence matrix. So incidence matrix said that if we have a graph which consists of V vertices and E edges, and it's an undirected graph with the vertices V1 up to Vn, and also their edges from U1 to UM, then we say that the incidence matrix with respect to the ordering of V and E is the N by M matrix. So here we can see the size changes. Remember, Mn is the size, is the number of vertices we have. M is the number of edges we have. So here we say the vertices were from V1 to Vn and the edges from U1 to EM. So incident matrix with respect to the ordering of V and E is the N by M matrix. Now we still put the 2 values, 1 and 0. If we have an edge, when an edge is incidence with VI, then we put 1. Otherwise, we put 0. So let's see an example. So here we have a graph with vertices from V1 to V5, V1, V2, V3, V4, V5. We also have the edges, U1, U2, all the way to U6. So when you look, remember we say n by m. So if the vertices are 5, it will be 5 rows. So let's count the rows. 1, 2, 3, 4, 5. Always in matrix, including mathematics, the size of a matrix is the number of rows first by the number of columns. So since here we have 1, 2, 3, 4, 5, it means we have 5 vertices, because the definition said n, the size will be n number of vertices by n number of edges. The number of edges is 6, if I'm not mistaken. 6 is the highest. So we have 1, 2, 3, 4, 5, 6. So it will be 6 columns. So we say the rows going from top to bottom represent the vertex, V1 to V5. And then the columns going from left to right represent the edges, U1 to U6. So now let's start with the first one. Why we get 1 here? I'm in V1. And when I'm in V1, I can say that I have vertex E1. From V1, we have vertex E1. Remember, we say the edges. When I'm V1, V1 is the vertex, E1 is the edge. So when I'm at V1, I have edges E1, E2, and I think that's it, E1, E2. So you can see that the rows are the vertex V1, V2, V3, V4 to V5. And the columns are the edges U1, U2, U3, U4 to U6. So this is incidence matrix. So why do we have 1 here? Because at vertex 1, we have U1, so that's 1. Why do we have 1 in the second column? Because at vertex 1, we also have U2. U2 is there, connecting to V2, so that's 1. Now that's it. The rest, there's no any edges no more from U3 to U6, so the rest is 0. Then I'll move to the second row, which means I'm in vertex 2 now. So when I look at vertex 2, do I have U1? No, so it's 0. Second column, do I have U2 to vertex 2? No, so it's 0. Third column, do I have U3 to vertex 2? Yes, so vertex 2 connect by U3. So I have 1. Also 4, I have 1. 5, I don't have it at V2, so it's 0. 6, I have it V2 to V3 is 6, so that's 1. Let's do the last row, which will be third one. So it's repetition. So when I'm in third, do I have U1? No, so it's 0. Second column, do I have U2? No. Third column, do I have U3? No. At vertex 3? No. At vertex 3, do I have U4? No. So everything is 0. But I have U5 and U6, so they are 5th column and 6th column. Then vertex 5, I will stand at 5. Yeah, I have a vertex. Sorry, we go to vertex 4 first. Vertex 4, we just did vertex 3. So vertex 4, I have U1, it's 1. But I don't have no U2, so it's 0. I have U3 to V2, so U3 is 1. I don't have no U4, I don't have no U5, I don't have no U6, that's it. And the last one, vertex 5, I don't have no U1, so it's 0. I have U2, 1. I don't have no U3, but I have U4 and I have U5, so they are 1, 1. I don't have no U6 at V5, so it's 0. And the same concept for the next one. First, we count how many vertices we have. 1, 2, 3, 4, 5. So we're going to have 5 rows. 1, 2, 3, 4, 5. The edges, it seems like it goes up to 8. 8 is the highest. So we have 1, 2, 3, 4, 5, 6, 7, 8. And the same steps. Let's do only 1 row. So 1 row means I will be in the first vertex. Second row means I will be in the second vertex. Third row means I will stand at the third vertex. So I'm going to start at the first vertex. Oh, this time I have a loop in the V1. So first row, first column will be 1. There's a loop. And that's U1 loop. Then from U, we also have 2. So 2, second column. And we also have 3, 1. So we have 1, 1. Then the rest, we don't have 4, 5, 6, 7. When we start at V1, there's no U4 connected to V1, no U5 connected to V1, no 6 connected to V1. no 7 connected to V1, no 8 connected to V1. So everything is 0. Then I'm going to the second row, means I will stand at V2. Do I have U1? No, U1 is a loop for V1 by itself. So at V2, I don't have no U1, so 0. Second column, do I have U2? Yes. Third column, do I have U3 from V2? Yes, so it's 1. Fourth column is U4. Do I have V2 connect to U4? Yes, so it's another 1. U5 is between V3 and V5, so it's 0 for V2. And 6 is 1, V2 to V5. 7 is still 1, V2 to V4 is E7. And 8 is a loop on V4, so it's 0. So we get 0. So again, we'll repeat this throughout the whole section. So that will be again the conclusion of these lectures. Maybe we should do one more. Let's do the last row. The last row means I will be in vertex 5. So in vertex 5, I don't have no U1, I don't have no U2, I don't have no U3, I don't even have no U4. So everything is 0, 0, 0. But I have U5 connecting V5 to V3, so it's 1. And also I have U6 connecting V5 to V2, so it's 1. Now I don't have no 7. 7 is connection between V2 and V4. It doesn't connect V5. And the last one, 8 is a loop to V4, so it doesn't connect V5. So it's 0, 0. So this will be the conclusion of our lectures. Again, these lectures will learn how we can represent graph as an adjacency list, and also as an adjacency matrix, and also as an incidence matrix. And we saw all the techniques used for it. So again, if you have any question, feel free to send an email, or you can also reach me on my telephone by texting. So again, wish everybody good luck. Thank you.